Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the ERNIE 4.5 technical report from Baidu, published in June 2025. Are you ready to explore one of the most advanced large-scale foundation models to date?
Absolutely. ERNIE 4.5 has been making waves in the AI community, and I'm excited to break down its architecture, training strategies, and evaluation results. To start, can you give us a high-level overview of what ERNIE 4.5 is all about?
Of course. ERNIE 4.5 is a family of large-scale foundation models, including both mixture of experts MOE and dense models. The largest model boasts 424 billion total parameters, with 47 billion active at inference. The family includes both language-only and vision language models, supporting text, image, and video inputs.
That's impressive. What sets ERNIE 4.5 apart from other foundation models like GPT 4.5, Gemini 2.5, or Llama 4?
The key innovation is its multimodal heterogeneous MOE architecture. Unlike traditional unimodal MOE models, ERNIE 4.5 supports parameter sharing across modalities, while also allowing for dedicated parameters for each modality. This means it can process text, images, and videos more efficiently and with less interference between modalities.
Interesting. So, how does this architecture actually work? Can you walk us through the main components?
Sure. The architecture consists of several core components: a heterogeneous MOE backbone, a vision encoder, an adapter for aligning visual and textual representations, and multimodal positional embeddings. The MOE routes text and vision features to separate expert groups, but also includes shared experts and self-attention layers for cross-modal integration.
I see. And for the vision encoder, they use a variable resolution vision transformer, right?
Exactly. The vision encoder adapts to different image and video resolutions, preserving aspect ratios and using 2D rotary position embeddings. For videos, they sample frames dynamically based on video length and available sequence budget, and even overlay timestamps directly onto frames for better temporal understanding.
That's clever. What about the adapter? How does it help with multimodal alignment?
The adapter projects visual features into the same embedding space as text, using spatial and temporal compression. For example, it compresses 2x2 image patches and halves the temporal dimension, making the sequence more manageable for the transformer layers.
And the positional embeddings? How do they handle the different modalities?
They use a unified 3D rotary position embedding scheme. For visual inputs, temporal and spatial positions are encoded separately, while text tokens use standard 1D RAUP. This allows the model to flexibly handle sequences that mix text, images, and videos.
That's a lot of engineering. Let's talk about the pre-training process. What kind of data do they use, and how do they manage such large-scale training?
ERNIE 4.5 is trained on a massive, curated dataset from web pages, academic papers, documents, images, videos, and synthetic data. They use a sophisticated data filtering pipeline to remove noise and deduplicate content, and even synthesize high-value data for domains like math, factual knowledge, and code.
How do they ensure the data pipeline is robust, especially with such large-scale distributed training?
They introduce REEAO, a bitwise deterministic pre-training data manager. It guarantees reproducible and non-redundant data access, even when training is interrupted or the cluster configuration changes. This is crucial for avoiding data duplication or omission during long training runs.
That's essential for stability. What about the pre-training stages? How do they structure the training for both language and vision language models?
Pre-training is divided into 3 stages. Stage I is text-only training, building a strong language backbone. Stage 2 is vision-only training, where the vision encoder and related modules are trained. Stage 3 is joint multimodal training, where all parameters are trained together on mixed text, image, and video data.
Do they use any special loss functions or optimization techniques during training?
Yes, they introduce two novel loss functions: router orthogonalization loss and token balanced loss. The router orthogonalization loss encourages the MOE router to specialize experts, while the token balanced loss normalizes the loss by sequence length, reducing gradient variance in multimodal settings.
And what about parameter smoothing? Do they use exponential moving average, EMA?
They do. EMA is used to stabilize training and improve generalization. They even provide a theoretical analysis showing that EMA acts like a form of implicit learning rate decay, and they propose a principled way to set the EMA decay window.
That's a lot of innovation just in pre-training. What happens during post-training?
Post-training is modality-specific. For language models, they use supervised fine-tuning, SFT, on a diverse set of tasks, followed by reinforcement learning with a unified reward system. For vision language models, they use progressive SFT and reinforcement learning with verifiable rewards, especially for tasks like visual STEM and UI2 code.
Can you elaborate on the unified reward system for RL?
Sure. For reasoning tasks, they use rule-based verifiers, reference-guided LLM as a judge, sandboxes for code, and discriminative reward models. For non-reasoning tasks, they use checklist-aware verifiers, generative reward models, and discriminative reward models. This ensures precise feedback for both reasoning and open-ended tasks.
And for reinforcement learning, they introduce progressive RL and unified preference optimization, right?
Correct. Progressive RL trains the model in stages, starting with logic, then math and code, and finally general tasks. Unified preference optimization integrates pairwise preference modeling into PPO, improving stability and reducing reward hacking.
What about the training framework? How do they handle such large models and multimodal data?
The training framework is built on paddle and features heterogeneous parallelism for multimodal training, hybrid parallelism for the MOE backbone, FP8 mixed precision training, and a framework-native fault tolerance system. They achieve 47% model FLOPS utilization on their largest model.
That's impressive efficiency. Can you explain the heterogeneous parallelism strategy?
The vision encoder is trained in data parallel mode, while the MOE backbone uses expert, pipeline, and data parallelism. They implement a hierarchical load balance strategy to handle variable resolution inputs, ensuring balanced computation and memory usage across devices.
And for memory efficiency, they use operator-level recomputation and flash mask for attention, right?
Exactly. Operator-level recomputation allows finer-grained memory savings, and flash mask reduces memory complexity for attention masks, especially in long context training.
What about inference and deployment? How do they make such large models practical to use?
They offer multiple quantization schemes including FP8, INT8, INT4, and even 2-bit quantization. Their largest model can run on as few as 4 GPUs with 4-bit precision or a single 141GB GPU with 2-bit precision. They also use prefill decode disaggregation for efficient inference, achieving up to 56K input TPS and 18K output TPS per H800 node.
That's remarkable. Do they provide open-source tools for training and deployment?
Yes, they open-source ERNIE kit for training and fast deploy for inference. These toolkits support industrial-grade workflows, low-bit quantization, and multi-hardware compatibility including NVIDIA GPUs, Kunlunkean XPU, Hygon DCU, and Ascend NPU.
Let's talk about evaluation. How does ERNIE 4.5 perform compared to other state-of-the-art models?
ERNIE 4.5 achieves state-of-the-art results across a wide range of benchmarks. For language models, it outperforms DeepSeek v3 and Qwen 3 on most general, reasoning, math, and coding tasks. For vision language models, it excels in visual knowledge, document and chart understanding, multimodal reasoning, visual perception, and video understanding.
Can you give some specific benchmark results?
Sure. On the CEval and CMMLU benchmarks, ERNIE 4.5 tan 3 hu half 3 sig 005 tan sur P847B FAF. It sees meeting the a Univica gain, then sends it to you. For Taquane all, it you'll have the 4942005 Tandani 424B54 take 48 data 4 data yo hive, surpassing DeepSeek v3. On math tasks like GSM 8K and math, it achieves over 91 and 69 respectively. For coding, it scores 84.8 on Human Eval Plus.
And for multimodal tasks?
ERNIE 4.5 DEL 424B54 Mr. 5. A Frukenche 451. Elna Parent EAL, Helloper 24, Gifian 5011, RV in the Kug, Agree Stobe, That Neo. RKK4. Doping to Orin, 6B Dietmel, Mahabala. Who are the list? 100 Teodoros, let this is a windy, flopping West 21B, A3B, and ERNIE 4.5 D0.3B models provide competitive performance with significantly fewer parameters, making them suitable for deployment on standard hardware.
That's great for accessibility. Are there any qualitative examples in the report?
Absolutely. The appendix includes examples of document understanding, OCR parsing, video temporal grounding, ancient character recognition, chemistry and math reasoning, visual pattern recognition, emoji quizzes, depth sorting, counting, common sense reasoning, code synthesis, and image-conditioned creative writing.
It sounds like ERNIE 4.5 is a truly versatile and powerful foundation model. What are the main takeaways from this technical report?
The main takeaways are: ERNIE 4.5 introduces a novel multimodal heterogeneous MOE architecture, achieves state-of-the-art performance across text and multimodal benchmarks, and provides open-source tools and models for the research community. Its innovations in training efficiency, quantization, and deployment make it a leading choice for both research and real-world applications.
That's a comprehensive summary. Before we wrap up, do you have any thoughts on the future directions for ERNIE 4.5 and large-scale foundation models in general?
The report emphasizes continued collaboration with the research community, further improvements in efficiency and scalability, and expanding the capabilities of foundation models to new domains and modalities. Open sourcing the models and toolkits will accelerate progress and innovation in the field.
I agree. The open-source approach is crucial for democratizing access to advanced AI technologies. Any final words for our listeners?
If you're interested in large-scale AI, multimodal learning, or efficient model deployment, I highly recommend checking out the ERNIE 4.5 models and toolkits on GitHub and Hugging Face. The technical report is a treasure trove of insights and engineering best practices.
Thank you for joining us on this deep dive into ERNIE 4.5. We hope you found this review informative and inspiring. Stay tuned for more paper reviews and AI discussions in our upcoming episodes.
To summarize, ERNIE 4.5 is a groundbreaking family of foundation models that leverages a novel multimodal heterogeneous MOE architecture, achieves state-of-the-art results across text and multimodal tasks, and provides open-source tools to advance research and deployment in large-scale AI. Thank you for listening, and see you next time.